2, 1, another Math 2070 online video. Alright, so last time we introduced the idea of linear independence and bases, and we kind of made a point that, hey, polynomials look a lot like Rn. We're going to make that idea a lot more formal today. So, given a vector space with a basis, b1 to bn, note that any element in your vector space is a linear combo of these elements, because that's what it means to be in the span. And a feature of linear independence is that these scalars must in fact be unique. Right, now that can be easily seen if you have a different set of scalars, then subtract the two equations, then you have a trivial linear combination of your basis elements, and there you go. So, because every element x in our vector space has a unique representation as a linear combo, we can take these scalars and note these are real numbers, and thus we can create an element of Rn that is uniquely associated to that element in the vector space. And we'll call these the coordinates of x relative to the basis and write it as follows. X, closed brackets, sub b, is the coordinates. So, for example, we know that the polynomials 1, t squared, t cubed are a basis for p3. And if we then look at the vector, the polynomial 7 minus t plus 3t squared minus 5t cubed, well, look at the coefficients. The constant term is 7. That's the scalar on that. The constant term, the linear terms, coefficients negative 1. Quadratic is 3, and the cubic is negative 5. So now we can formally take polynomials and represent them as elements of P3. That means we get an R4. As we noted, the number of elements in the basis is one more than the P sub n. Alright, nice. So there we go. We now have done formally what we verbally pointed out, that, hey, polynomials really seem like they should be representable as vectors in Euclidean space, and here's how you do it. Hey, great. Well, now that we got this, what else can we do with this? Right? There we go, right? We kind of set it up, and now we have it, but now kind of maybe part in your brain's like, alright, well, what else can I really do with this? Well, something we saw in Rn was that there's more than one possible basis. And as we mentioned and kind of saw, right, you can set up matrices that have to have bases that are something other than the standard basis elements. And different bases are going to have different powers and uses depending on the context. Right now, for the polynomials, all we have is the standard basis. Now note that this is basically the standard basis in Rn, just recodified for polynomials. It'd be great if we could construct and work with other polynomial bases. Right, we know we can do it for Rn, so how do you do it for polynomials? Well, let's go to Rn for a second and play around with these coordinate vectors. So, let's say you got a basis for Rn. We know that that list of elements will create a invertible matrix, right? We noted an invertible matrix makes a basis, and vice versa. So if I take an element of Euclidean space, how do I find the coordinate vector for it? Well, let's let P sub b be the matrix who has the basis elements as its columns. Columns as its column. Get out of here. Alright, well, if I do that, note that x, which has to be a linear combo of b1 to bn, where the c1 to cn is the coordinate vector, well, these are the columns of this matrix PB. These are the elements of x sub b. So, hey, wouldn't you know it, this linear combo is this matrix multiplication. And as we noted, this is a big fat invertible matrix, because those columns are linearly independent. There you go. If you want to compute a coordinate vector in Rn, you take your original vector and multiply it by the inverse of the matrix P sub b, where P sub b has the basis elements as its columns. Naturally, then we'd call P sub b the change of coordinates matrix. Alright, so let's see this in action. Hey, those look familiar. Almost as if we already proved that that was a basis. Its change of coordinates matrix is the matrix that has its columns, and its inverse is that. Remember, for a 2 by 2, inverses are quite nice. We already demonstrated that the determinant of this matrix is 1. So the inverse then is found by swapping the diagonal and negating the off diagonal. So, equipped with this, you can compute the coordinate vector for any vector in R2. So, for example, if I take this one and I multiply by the inverse, I've got its coordinate vector. And here's the great news: we can check our work. Remember, these should be the coefficients, so that scaling and adding these will give me x. And you can check that. So if you take 1, -3, multiply by 8, and add 2, -5, multiply by -5, here you'll get 8 minus 10, -2. There you'll get -24, positive 25, big fat 1. Beautiful, we did our work correctly. So, it's always great when you got a math problem that you can do some work, you get your answer, and you know how to check it and make sure that what you actually got is correct. Right. And of course, when we mean that, we always mean like a different way of checking, other than like, hey, I did the work, it should be right. Well, if you have this sort of external test, which we have here. Beautiful. All right, now that I have this, let's talk about coordinate vectors, again in the context of vector spaces. And again, right, kind of in the back of our mind right now, we're looking to see how we can play around a bit more with other, maybe more interesting bases for polynomials. The coordinate mapping is the function that takes an element of a vector space and sends it to its coordinate vector. Right, if you have a basis, then you can create this function. It doesn't take too much effort, but you can prove that T is an invertible linear mapping. Right. The linear part takes maybe not too much crazy effort, but just imagine if you have an element, you scale it, well, then you would just be scaling the coefficients on the linear combo for the basis element. So, hey, you're just scaling by the number, so you can just pull it out. Likewise with sums, you're just adding up the coefficients. The one-to-one is hopefully easy to see. If it's linear, one-to-one happens if you can only send 0 to 0, and the only thing with a 0 coordinate vector would be the additive identity of the vector space. On2 might be a little bit more tricky, but just pick any element of Rn and then scale your basis elements, and that gives you the thing that maps to it. So an invertible linear mapping, we've already used this word a few times, but it's worth noting that a fancier term for this is a linear isomorphism. And the power of a linear isomorphism is that it tells us that any vector space with a finite basis is essentially the same thing as Rn. Right, now, why is that true? Well, the linear is telling me that the scaling and the adding of the vector space carries over to the scaling and the adding of Rn. So, in other words, the linear part tells me that scaling and adding in V is the same thing as scaling and adding in Rn. The invertible part tells me that there is a one-to-one correspondence between the elements of V and the elements of Rn. So, the scaling and adding, the vector space structure, is preserved, and the invertibility gets me that as sets of math objects, these are exactly the same. So, these are functionally the same thing, even though they may have different presentation. Like, oh, I don't know, maybe the things in V are polynomials. So isomorphisms are a very powerful tool in mathematics. You've maybe unwittingly been using them your entire life. But before we move on, I have a fun story about the word isomorphism. So I was at a conference at the Southern Illinois University at Edwardsville, and we were heading over to lunch, and we walked by this like open area, and there, for whatever reason, there was an Elvis impersonator doing his Elvis impersonator thing, and he had a good gimmick. He had a gimmick that, like, he was an Elvis impersonator, but he recognized that Elvis was dead, and so, like, he was like the ghost of Elvis that, like, became corporeal for a second so he can perform for you. It was pretty good. I thought that was a mildly clever. Just like, he's not just like, hey, I'm being Elvis. Like, I am literally Elvis. Like, it's pretty funny. And anyway, so we're watching him, and one of my buddies, Professor Lausch Molnar, comes up, stands next to me, and we're watching Elvis for a little bit. He nudges me, and he goes, "Hey, Chris, this isn't Elvis." This is isomorphic to Elvis. So if you want a good relatable thing to what a linear isomorphism is, it's essentially an Elvis impersonator. So I laughed super hard at that joke. By the way, I was like, I almost fell over. It was great. Good joke. Roll on snare drum. All right, but moral of the story is that because we know that any vector space with a finite basis is essentially the same thing as Rn, anytime you have a problem in your vector space, and you know you got a finite basis, bring it over to Rn and solve it there, right? Because over there, we're going to have vectors, we're going to have matrices, we have all of those tools to help us do computations. So consider the polynomials 1 plus t, and 1 plus t squared. Okay. We can directly verify these are linearly independent by scaling and adding them up, setting it equal to 0, distributing terms, getting equations for the coefficients, and solving it. However, we know that these things are really elements of R3. Right, it's P2, it's a second order polynomial, so we have to include the constant term in the count. So hey, each one of these is this element of R3. Smash them together into a matrix. It's super easy to see that this is invertible. Its determinant is 1. It's an upper triangular matrix. So the product of the diagonal entries gives us 1. So, hey, this is an invertible matrix, which means that these coordinate vectors is a basis for R3. But as we already noted, R3 and the polynomials of degree -2, they are essentially the same vector space, so that means that these original polynomials have to be a basis for P2. So not only do I immediately know that these are linearly independent, I also know that every polynomial in P2 can be written as a linear combo of these. So the power of the coordinate vector is telling me that if I've got a problem, I'm interested in these polynomials, carry it over to R3, check for their invertibility, I now know that they're a basis, so I could do cool stuff. And in fact, if I let h equal this, I know this is a basis, which means I can compute coordinate vectors in this new basis. So if I ever needed to get a polynomial as a linear combo of these, which, again, these might be more useful for whatever your particular application is, I now know how to do that. Because each one of these elements can be represented as, there should be a 0 right there. That is very much not an invertible matrix. Oh boy. Anyway, all right. Fixed the 10. What? No. Oh boy. All right. The inverse is correct. The original matrix is not. There we go. Anyway, so these elements we know can be represented as 1, 1, 1, 0, and 1, 1, 1, and R3. So we can make the change of coordinate matrix for those and get its inverse. So now let's show how we can take this polynomial and create the coordinate vector with respect to this basis h. Well, first we convert it over to a polynomial in R3, a vector in R3, taking the polynomial and converting it over. All right, well, hey, if I want to get this in terms of its basis element with respect to the basis h, I multiply this by the inverse element, the inverse of pH. And if I do that, I get this. And again, we can check. We can do the computation. These should be the coefficients on the polynomials 1, 1 plus t, and 1 plus t squared that give me this polynomial when I scale and add them up by these coefficients. And indeed, we see that that does happen. So note the constant term will be 25 minus 7 minus 13. That is indeed 5. The t term needs to be 12. Here I have a positive 25 and a negative 13, so I get 12. And my t squared needs to be, negative 13. Perfect. There we go. Now we know how to represent any polynomial with respect to any basis going on. You just got to convert it over to Euclidean space and work with it there. Good stuff. All right. And that is coordinate systems. Beautiful. I'll see you in the next video.